every time you prove something that we're going to talk about, there's always a given, there's always something I give you, and then there's always an end result. There's always what you're trying to prove. How you get there, it doesn't matter, as long as you follow certain rules. The rule here was that every word had to be an actual word, right? It doesn't matter how you get there, as long as you follow it's logical how you got there, you follow some sort of rules. But there's always a given, and there's always something you're trying to prove. In this case, I gave you cat, we're all trying to get to dog. Every proof is the same way. Here's a given, I want you to show me this or prove this. The steps you take to get there can be different as long as they're logical steps, and I'll show you the steps that you can use, then that's fine. Okay, you get to the same result. What a proof is. And the actual definition of a proof is it's a logical argument where each statement you make is supported by another statement that's accepted as true. If you're trying to prove something to be real, just in anything, not geometry, you have to make a logical argument and you have to give supporting statements that are accepted as true, right? It's the same definition here. Some of those supporting statements we call theorems. Theorems are a statement that are a conjecture that has been shown to be true. So you can use a theorem as justification, as a reason to prove something. That postulate sheet I gave you has a list of the theorems, has a list of postulates that you can use to prove things. Those can be your justifications. Those can be your reasons. Okay? When you make a statement, you can back up your statements with those postulates, with those theorems. Those are things that are accepted to be true. Postulates and axioms are things that are accepted as true and you don't have to prove them. You can use them as reasons. So we're going to go through those on your postulate handout here one by one and talk about those. You had 2.1, which is on there. It says through any 2 points, there's exactly one line, right? That makes sense. Anywhere you put 2 lines on a plane, there's only one line that goes between them, right? I can't draw 2 different lines that goes between these 2 points, right? There's only one line that exists that go between those 2 points. Right? That's a true statement. That's accepted as true, okay? And this is a reason that you can use to back up other arguments, okay? We'll get to those after a while. So that's the first one. The second one, when you have any 3 points that are not on the same line, that are not collinear, there's only one plane that goes around them, okay? Think about that. If you just put 3 dots on your desk, there's only one flat surface that you could put that contains all 3 of those dots, right? You couldn't draw 2 different planes that contain 3 non-collinear points. There's only one plane that goes around it. That's 2.2 on your sheet. Okay? These are all on your postulate sheet. You don't have to write these down. Okay? 2.3, if you have a line, then it has at least 2 points. Really has infinite amount of points because it goes on forever, but you have to have 2 points to make up a line. You can't make up a line with just 1 point, right? I don't know what line this is. Is it that one, that one, that one, that one, whatever? You have to have at least 2 points to make up a line. Really, there's an infinite amount of points, but at least 2 have to exist. You can't have a line that exists with just 1 point. Okay? 2.4, if you have a plane, it is made up of at least 3 points that are not on the same line. So you have a plane, it's made up of at least 3 points that are not on the same line, right? If I have a plane here, it has to contain at least 3 points. You can't have a plane that contains 2 points. That would be a line, right? A plane has to have at least 3 points that aren't on the same line. And then 2.5, if 2 points are in a plane, then the entire line that contains those points is also in the plane, right? If I have 2 points and they're part of a plane, then the line that goes through those 2 points is also part of the plane, right? That makes sense. If the 2 points are in the plane, the line that goes between them is between the plane. 2.6, if 2 lines intersect, then they cross at exactly 1 point. So I have these 2 lines that intersect, okay? Therefore, they cross at 1 point, right? You can't have 2 lines that cross and they cross at multiple points because those would be curved lines, right? If 2 lines cross, this is if they cross, they don't have to cross, right? But if they cross at 1 point. They can't cross in 2 points. It's impossible, right? And 2.7, if 2 planes intersect, now they don't have to intersect. If 2 planes intersect, then they intersect in a line, right? So if I have 2 planes that kind of cut each other like that, if they cross in a line. Now, so if you look at like these 2 planes, if I call these 2 sheets of paper planes, right? They don't have to cross though. If I just went like this, remember planes go forever in every direction, they're just flat. They don't have to cross. We could call them parallel, right? But if they do cross, they cross in a line, right? Even if they're like this, all the sides go on forever, they would still cross in a line, right? A plane can never cross in a point. It has to cross in a line. If it crosses, they don't have to cross them. Okay? So that's all those postulates, and then you had one theorem there underneath those on that sheet. And that was called the midpoint theorem. The midpoint theorem says that if M is the midpoint of a line segment AB, so I'm going to draw this picture out. If you have a line segment AB, and I told you M was the midpoint, then A to M is congruent to M to B. We know that to be true, right? If that's the midpoint, that means that chunk's equal to that chunk. We already knew that. Now we have a theorem that we can use to help us prove things to be true. Okay. So looking at your theorems, I want to go through a couple of these, and we want to look at, are these statements always, sometimes, or never true? Okay. So looking at your theorems, I want you to look at this statement and determine, is this always, sometimes, or never true? So it says plane T, so let's draw a picture. If plane T contains line EF, and line EF contains point G, is it always true that plane T has to have point G in it? Is it sometimes true, or is it never true? I'd agree, always. Why?
Because plane T that has the entire line in it.
Exactly. What theorem is that? I don't have it in front of me. I really don't know off the top of my head. What's the number? 2.5 says the entire line's in that plane, therefore point G is also in that plane. So I would say this is always true by theorem 2.5. You don't have to actually write the theorem out in words. You can give me the number. Okay? That's always true. There you go. Theorem 2.5, if 2 points lie in a plane, then the entire line containing those points lie. That's your justification for that. That's your reason, your supporting argument. Okay? How about this? If you have line XY, and X lies in plane Q. So X is here, and I have another plane called R, okay? And it has point Y, and I have line XY. Is it always, sometimes, or never true that plane Q intersects plane R? Well, in my picture, if you looked at that, it's kind of hard if you thought of it. But these two could be parallel, right? You could have two planes that go like this and never cross, and you could have a line that runs between them, right? So they don't have to intersect, but the two planes could intersect, right? So I would say this is sometimes, because the planes could be parallel, and XY can go through both planes. That statement is sometimes true, because the planes could be on top of each other and not cross, or they could cross, right? They don't have to always intersect. How about this? Is this always, sometimes, or never true? Line GH contains 3 non-collinear points. Always true, sometimes true, never true. That's never true, right? Non-collinear means that they aren't on the same line. So you can also use definitions to help you prove things. Non-collinear means not on the same line, so that's never true by the definition of non-collinear, because non-collinear says they're not on the same line. So you don't have any definitions on your postulate sheet, but you can use those to help you prove things as well. How about this? Always, sometimes, or never true. Plane A and B intersect in 1 point. Never. Because if they intersect at what? A line. That's a postulate, right? So that's never true. If the planes intersect, they intersect at a line. That's a postulate you have on your page. Okay? We talked about this one earlier. This one's always similar too. 2 planes will always intersect to form a line. Always, sometimes, or never true. Sometimes. If they intersect, it's at a line. That you have a postulate that says that. But they don't have to intersect. They can be parallel. Sometimes they would intersect to form a line. Okay. Now let's talk about writing proofs. So you don't have to, these steps aren't something you necessarily follow every time, but a good proof, you always state what you're going to prove, what you're trying to prove. You always list what's given to you. You draw a picture if you can. You state what's to be proven, and you develop some reasoning behind it. You give supporting evidence. Okay, to review these properties real quick. Remember, you probably talked about these properties a long time ago. Reflexive, symmetric, transitive, addition, subtraction, multiplication, division, substitution, distributive. Okay, so let's talk about these properties, what these mean. Reflexive property, because these are also reasons you can use to prove things. Reflexive property just says something's equal to itself. 3 is equal to 3. If I said prove that 3 is equal to 3, you could say 3 is equal to 3 by the reflexive property. Okay. Something's equal to itself. That's the reflexive property. 5 is equal to 5. X is equal to X. Reflexive property is very easy. Okay. Then we had, next one was symmetric property. Symmetric means it's the same on both sides, right? Symmetry. So symmetric property says if 3 plus 2 equals 5, then 5 equals 3 plus 2. Symmetric property just says you can switch what's on each side of the equal sign. Okay? That's symmetric property. You can switch what's on each side of the equal sign. So if I told you you're given that 4 plus 3 equals 7, prove that 7 equals 4 plus 3. You could say, well, 7 equals 4 plus 3 by the symmetric property. Okay? The symmetric property says you can switch what's on each side of the equal sign. That would be your justification, your supporting evidence. Okay? Next, you had transitive property. So transitive property is what we talked about with KU should have been national champs, right, in football. Remember that thing? It said if one thing was equal to another, or better than, and that thing was better than something else, then the first thing should have been better than that, right? Like we said, in this case we're talking about better than. KU beat Iowa State. Iowa State beat Iowa. Therefore, KU would beat Iowa. All right, that's a transitive property. Doesn't really work in sports. But, okay, that would be the transitive property. If one thing is equal or better than another, and that thing is equal or better than a third thing, then the first thing is equal or better than the third thing. Okay? We call that the transitive property. So a proof of that would be if I said, we're just doing real easy algebra proofs here. If 2 plus 5 equals 7, and 7 equals 4 plus 3, prove that 2 plus 5 equals 4 plus 3, right? And you would say, well, 2 plus 5 equals 4 plus 3 by the transitive property. That's the definition of the transitive property, right? If the first and second thing are equal and the second or third thing are equal, then the first and the third thing are equal. We call that transitive property. Okay? These properties, addition and subtraction, multiplication, division, you've been using forever. That just says if you add one thing to one side of the equal sign, you could add it to the other. If you subtract one thing on one side of the equal sign, you can subtract it from the other. If you multiply one thing on the equal sign, you can multiply it to the other. Okay? Anytime you do that in a proof, you have to say why. You have to say, I did it by the addition property. I did it by the multiplication property, something like that. Substitution property is exactly what it sounds like. It's just substitution. So I said, if x equals 4, prove that x plus 9 equals 13. Right? You've been doing this, but now we're just going to give you reasons for it. We're going to back it up with reasons. So you could say, well, 4 plus 9 equals 13 by substitution. You substitute in what was equal, right? And then 13 equals 13, okay, because you just did addition there. So that's true. You proved it. Okay? You just substituted it. So you've been using substitution for a long time. Distributive property, we've been using distributive property too. Anytime you distribute something, one term that's on the outside of two terms being added or subtracted together, you can use distributive property. Okay? Remember when I said you're given, in a proof, you're always given something and you always have an end result. You're always given something and you always have an end result. So what you're given is that AC, so I'm going to draw a picture, AC intersects CD. Since point C is there, that's the point of intersection. Okay. AC intersects CD. That's what's given to me. So there's what my picture looks like. I want to prove that this is a plane. ACD is a plane. Which theorem could I use to do that or which postulate could you use on your postulate sheet to do that? Looking at that picture, which postulate could you use to show that's a plane? 2.4 says what? Exactly. Very good. I could say ACD is a plane by 2.4 because 2.4 says a plane contains at least 3 non-collinear points. Are these 3 points non-collinear? Yes. So therefore they make up a plane by 2.4. That's my reason. That's my justification. I backed up my argument. I backed up what I'm trying to prove with a postulate. That's what you have to do every time. I want to show you're given, so let's draw out the picture of what we're given. You're given that M is the midpoint of PQ. I want you to prove that this piece is the same as this piece. All right? With me there? Let's change this to congruent too. I want you to prove that those are congruent. Okay? So I could say, if M is the midpoint, remember I'm going to state what's given to me. If M is the midpoint of PQ, then what? What's a logical argument I could make and back it up with a reason? Yeah. No. Go ahead.
PM congruent to
Yep.
MQ,
By what?
2.1.
Exactly. By theorem 2.1, which is the midpoint formula. Or sorry, the midpoint theorem. The midpoint theorem says if you have a midpoint, then both those segments are congruent. So there's my proof. I just proved that to be true, backing it up with a reason. Okay. If M is the midpoint, then PM is congruent to MQ by theorem 2.1, which is midpoint theorem. Let's look at another proof here. Again, every proof always gives you some information and tells you what you're trying to prove. Okay? If you can, I'd recommend drawing out a picture. Now, there's a lot of different ways to draw out this picture. This is one of them. It doesn't matter how you draw it, you're still going to prove the same thing. So, what's given to me? It tells me point L is the midpoint of JK. It also tells me JK intersects MK at point K. And it tells me that MK is congruent to JL. I want to prove that LK, this piece, is the same as this piece. So let's go one by one each step here. First, if point L, so I'm going to rewrite what's given to me. If point L is the midpoint of JK, what is this piece of the given information trying to tell me? This top line. Point L is the midpoint of JK, therefore what? When it tells me it's a midpoint, what's it trying to tell me? What's it trying to tell me is true? That what's equal? What's congruent? Right, exactly. That JL is congruent to LK. How do I know that? I have to give a reason for it. I can't just write it down. What's my reason? Exactly. By theorem 2.1. Right? So I'm going to mark those congruent in my picture. Everybody agree with that? Okay? I just use this part of my given. 99% of the time, whenever it tells you something in a midpoint, you're going to tell me which two segments are congruent by 2.1. That's a theorem. Here's your argument. Here's your justification. There's what's true. Let's look at my next part. JK intersects MK at K. I already drew that picture, so I drew that. That's what that told me. The next part tells me MK, this piece, is congruent to JL. So this piece is congruent to this piece, JL. And I'm going to mark those with a different color here. Let's say I mark those with red. What I'm trying to prove is that LK, this piece, is the same as this piece. Let's say we put some numbers to it. If, let's say the blue markings, let's say that was 3 inches, therefore that had to be 3 inches. And if this was, we said that was 3 inches, which means that has to be 3 inches. So how can I prove, what justification can I give that LK is congruent to MK? So let's think about this. What's the reasoning? I said the first and the second thing are congruent. The first and the third thing are congruent. So how can I prove the second and the third thing are congruent? What reason, property, theorem, postulate tells me I can do that? I said the first and the second thing congruent. The first and the third thing are congruent. Therefore, the second and the third thing have to be the same. That one's not on your postulate sheet. That's one of the properties we talked about. What property is that? Remember KU football? What property is that? Right, by transitive property. Right? Transitive property says if you have a first and a second thing the same, and the second and the third thing are the same, then the first and the third thing have to be the same. Here I have those two blue tick marks are the same, those two red tick marks are the same, therefore these two have to be the same by the transitive property. So I just proved that using my justification of theorem 2.1 in the transitive property. That's a good proof.